In the previous two videos, we solved two problems using weighted hierarchies method and least square method. In both of these examples, we used a specific type of boundary conditions. Those were essential boundary conditions, and that too were homogeneous essential boundary conditions. That is, the value that we specify for u or for the state variable was 0. Okay, so what we in both the examples we did the same thing. We just specified essential homogeneous type of boundary conditions. So in this next two videos, we are going to look how to implement non-homogeneous essential boundary conditions and also how to implement Neumann boundary conditions. Okay, so first we'll start with non-homogeneous essential boundary conditions. Okay, so we have seen this slide before. So we have two types of boundary conditions. Those are Dirichlet and Neumann boundary condition. In Dirichlet, we specify the value of the state variable. Okay, the dependent variable. In the Neumann, we specify some kind of derivative of that dependent variable. Okay, and these in the previous example, what we have done, we have constructed the basis functions such that their values at the point where the essential boundary conditions or the part of the boundary where the essential boundary condition has been specified was set to 0. Okay, this statement in the both of the examples that we have discussed so far, all the example 1, 2 and 3, what we have seen is this, what we have imposed. Okay, we just have a idea why did we do that, because we did it because we already knew that information that whatever solution that we are going to get, it should satisfy these things. We knew this thing beforehand, so we should construct our trial solution in such a way that the trial solution must satisfy these things. Okay, so we'll look this idea of having 0 values of the basis functions at the essential boundary. Why does it has to be like this? We'll look this thing into detail. So why this? Okay, let's start with taking an example such in which the Dirichlet boundary conditions are like this. These are homogeneous essential boundary conditions. Okay, we are specifying the state variable and their values are 0. That's why they are homogeneous. Okay, now we construct a trial for a solution something like this: the linear combination of C and the various basis function of your trial space summed over J. J varies from 1 to n, where n is the dimension of your space. Okay, dimension of the trial space. Now let's take just 2 dimensions. So we can write the trial solution as something like this. Now when we evaluate the trial solution at 0, we can write this this is the function of x, right? So I1 and I2 are the function of x, so we need to evaluate them at x is equal to 0. Okay, so we get one equation. Similarly, we can do it for x equals to 1. We get another equation. We can write these two equations in a matrix forms, something like this. Okay, in simpler notation, we write them like this. Okay, now let's see. What we want to prove is this psi, okay, this psi i's, the psi 1 and psi 2 should be 0 at x equals to 0 and x equals to 1. This means this matrix, this complete matrix, this matrix should be a 0 matrix. All elements here should be 0. Okay, in this case. Okay, when C is equals to 0, okay, for this product to be 0, either this thing should be a 0 matrix or this thing should be a 0 vector. Okay, now for this to happen, this C j's can't be 0, all 0. This is not possible, because otherwise you don't have a trial solution itself. It's 0. Already we have a solution, that's 0 solution. So it's a trivial solution for this equation. Okay, so we are seeking for a non-trivial solution. A non-trivial solution will be what? And this matrix is a 0 matrix. Okay, for a non-trivial solution, c is not equal to 0 and psi is equals to 0. Okay, so each element in this matrix is nothing but a 0. Okay, that's why if you want to impose, if you want these conditions to be imposed, if you want your trial solution to satisfy this condition, it is essential that your basis function should be 0 at those points, okay, at which the essential condition has been specified. Okay, so this is now out of the picture. We just know that we need to keep in mind that this has to be satisfied in any condition. Okay, now so far what we have discussed were the homogeneous boundary condition. Now let us look into how to satisfy non-homogeneous boundary condition. Okay, so let's start something like this. Okay, this is what we have been doing so far, and we have demanded that basis function should have 0 values at these points. All the basis function, psi1, psi2, psi3, psi4, doesn't matter how many basis functions that are using, every basis function should be 0 at the boundary at which this Dirichlet or the essential boundary conditions has been specified. Okay, so this is what we proved in the previous slide. Now, what about this kind of boundary condition where the value is not 0? This is non-homogeneous. D is not equal to 0 now at u equals to u at x equals to L. Now, what's the problem with this? So when you calculate the trial function at L, you get this. Okay, but these all are 0 because at this point we have specified an essential boundary condition. It doesn't matter whether this is homogeneous or non-homogeneous, but since we have specified an essential boundary condition, this is 0. All of these things are 0. So, but the value should be D, but it's 0 now, so we have a problem. So how do we compensate for this? We add an additional function, bx to uh. This function is called a boundary function. What property does this function satisfy? It satisfied bl is equals to d, and that is at the x equals to L, the value of this function is t. Okay, that's all that is required from this function. You can construct the way any fancy way you want. You can construct this basis function. Obviously you need to satisfy some differentiability requirement, but still you can construct. You are free to construct this basis function, this boundary function, and now our trial solution is this term bx. This is a boundary function plus our old linear combination of the cj's and the psi-j's. Okay, so now let us think how does this addition of boundary function changes our understanding of the space and the solution that we are looking in that space. Okay, now this is our approximate solution. Now this bx part is completely defined, you know that. Okay, that's what you have defined. You completely understand what this is. Our only unknown is this part. This is unknown, and also in this part the specific unknowns are the cj's. Okay, you are deciding what psi-j's are, you just need to find out the cj's. Okay, to construct. So how are we searching for our solution now? Where should we search? Because the trial solution is now something plus this linear combination. So the thing is, now our trial solution doesn't lie in the space V, whose basis function are these psi-j's. Okay, now our solution now doesn't lie in this space V. So in fact this trial solution doesn't lie in any space. There is, I mean, if you think mathematically, if you want definition or mathematical definition of a vector space, this doesn't follow the rule of close scalar multiplication and addition that is required for space to be qualified as a vector space. So we won't go much deep into that. So the thing that we know right now, it doesn't lie in the space V, okay, because but this thing in this thing in the box, it lies in that space, okay. So we write this thing as this, okay, some uv of x, okay. Now this thing actually lies in the vector space and it is a part of our trial solution, okay. So given bx, that's what we know, we try to find out this uvx that lies in the space V, okay. Now we are finding a part of the solution, not the complete trial solution. We are just finding the part of the exact solution, that is uvx now, okay. So now everything that we have studied till now, looking in the space, the dimension of the space, everything that now applies to just this uvx. And our actual solution, we don't know where does it lie, actual trial solution, okay, not the actual solution. It might be lying in some infinite dimensional space, but this trial solution, we don't know, it lies in some vector space, or maybe it doesn't lie. The later fact is that is actually true, it doesn't lie in any space, okay. There is no, I mean, if you think of closeness under multiplication and addition, scalar multiplication addition, it doesn't qualify to be an element of a vector space, okay. So now we know that this is what our problem now is. Just to figure out this, we need to find out CJs. To find out CJs, this same thing, we are looking to solve this problem to find out CJs, and CJs are the basis function of some space V, okay. Note that UH minus B now lies in V, not UH, and UVX is this. This is our new problem. This is what happened when we added the BX, the boundary function, okay. Another thing that we'll see in future, it won't make complete sense right now, but in FEM there will be no need to construct such kind of boundary function. I mean, you need not do it yourself. We'll construct such basis function, okay, that will be automatically in some will be automatically in position to satisfy non-homogeneous boundary conditions as well, okay. We'll see that when we start discussing FEM, but just to keep in mind this that's what one of the advantage of FEM is. You need not construct such boundary function to satisfy non-homogeneous essential boundary conditions, okay. Now let us see another example 3, where we try to satisfy non-homogeneous Dirichlet boundary condition, okay. So this is the problem. The second order differential equation that we want to solve in this domain. These are the non-homogeneous essential boundary conditions at the two boundary ends, and after using the Galerkin's weighted residual method, residual inner product with the V, okay. Now V is the space in which we are looking for the UV part of the solution, okay, the part of the solution, not the UH, okay. So this is what the residual statement is, and UH is now B plus Cj psi j summed over J. Now let us construct our boundary element. We are constructing this. Let us construct it something like this, okay. You can check that at x equals to 0 C and x is equals to L, okay, it is D, okay. B at 0 is C, B at L is D, so it qualifies to be a boundary function. Now we can simply, just for simplification of the calculation, we write this part as m. Okay, that is the scalar value. Now the first and the second derivative of the boundary functions are m and 0. Okay, now sorry, there should be a double dash here and it should be a UH here. Yeah. Now, okay, so UH dash is this, UH dash we have written, UH double dash is something like this. Okay, just from this expression we have written this, and from this we are writing this. Okay, so let us write this expression. Just put the values of the UH dash and UH double dash here. This is a correction. Okay, when you put this, UH double dash is here, UH dash is here. Okay, this part is UH dash, this is UH double dash, and now the basis functions are psi I. This is where this part lies. Okay, this lies in V. Now, just after we have separated m, we have brought everything together inside the summation, these two terms. Okay, and distributed the inner product over m and this term. Now we just take that side and just since this is inner product with m, so again bringing these f and m together here and taking the Cj out. That's what we have been doing for all the examples. Okay, so now this is what finally is the set of equations that we are going to solve to calculate these Cj's, where Aij looks something like this and Bi looks something like this. Okay, the extra addition is m. You see, from the boundary function part you get in this B vector this m. Okay, here is what is changed because of the boundary function. Okay, now let's see the implementation of this thing in MATLAB. Yeah, so this is the equation that we wanted to solve. Okay, and this was the non-homogeneous boundary condition. So similar to the previous example, we start with declaring the symbolic variables. We declare our function. Okay, this is some random function that I have chosen. Okay, in this equation, some f of x. This is some complicated, this some random thing, and we solve this ODE to get the exact solution to compare it with our trial solution. Okay, now we choose basis functions, something we are using the same sinusoidal basis functions. We could have used some another basis function, but we don't want to demonstrate here the selection of basis function, just how to the use of the boundary functions. Okay, so this is what we have developed just in the previous slide, these Aij and Bi, and we calculate them using this psi I, psi id, psi double d, and this is our basis functions. This is the bs, this one, this is the as, this is a, and again we convert these symbolic functions to matrices and vectors in this, okay, by looping over ij. Now we solve for the coefficient here and we construct our solution like this. Okay, again we need to convert this symbolic function to a vector here, ps, psud and ps for first derivative, second derivative, and the value of the basis function. Okay, this is the correction if required for power 0 to 0, and again we construct our u as something like this. This is the boundary function, this part bx, and this is cj psi j, the summation. Okay, so also we can calculate residual similar to the previous examples, and we can plot the results. As you can see, these are the real results that I've already plotted. You can see our problem was at u goes to 0, it should be equal to c. Specified was c and a, c 5 and minus 2. Okay, at 0 it is 5, and at 4 it is minus 2. Okay, the error is quite big right now because the dimension that we are using is 1. The result should improve when we reduce the size. Let us do that in a bit, but before that I might need to have not actually doubled it, the error to error is double. I'll take this thing. Okay, and I'll plot error. Here. Okay, let's now try to run the code. Let us use 4, n is equals to 4. I hope there is no bug. Right now it's doing this. Okay, we have some issue. Line 859. Okay, so here also we need to convert it into a double. Let us rerun. It's only mainly in the time that this code takes. Most of the time is consumed in this line. Oh, again. It should be positive integers. This is our division. That's what we have been doing. We see that example 2. Okay. Getting error in this line, right? What is the error? U sol x is double. There's no problem with this. Okay, I think the problem is we have not defined it as a function of x. That is why. Okay. Yeah, now it solves. Again, see, even by using analysis 4, the solution is not that good. Let's go to extreme 8. You will see most of the time it will take here in this line, B and A. Pretty complicated functions, these two. is almost the same, following the exact solution, and the error is also pretty low as compared to the magnitude of u. Yeah, so that's it for this video. It was a bit long because of the errors that we found in the code. So that's it for this video. We'll see implementation of Neumann boundary condition in the next video. Thank you.